Question 5 says an aluminum cup contains 225 grams of water and a 40-gram copper stirrer, all at 27 degrees. A 420-gram sample of silver at an initial temperature of 87 degrees is placed in the water. The stirrer is used to stir the mixture gently until it reaches its final equilibrium temperature of 32 degrees. Calculate the mass of the aluminum cup. This question almost sounds like I eat snow ice cream and drink coffee, so figure out my favorite TV show, something that's unrelated, but it's not that bad. It's actually it's the thermal equilibrium expression that has been on every question so far. So Q1 plus Q2 plus Q3 plus Q4 equals 0. So it doesn't matter how many different items you have in here, the sum of all of their transfers of energy within an isolated system will always equal 0. And so we could keep adding a Q5 and a Q6 and a Q7 all the way up ad infinitum, but we just have 4. So we need to solve. We're going to call Q1 the cup, and then Q2 is going to be our water, Q3 is going to be our stirrer, and Q4 is going to be our silver. So just write that down. Q1 is the cup, Q2 is the water, Q3 is the stirrer, and Q4 is the silver. There's a couple ways to do this. We could isolate Q1 by subtracting it to the other side. I wasn't smart enough to think of that initially, so I subtracted all Q2 through Q4 to the other side. So I'm just going to go ahead and work it like I worked it originally. Q1 equals the negative of Q2 minus Q3 minus Q4. And so remember, the only thing that can be negative inside of the expression of Q, mass times specific heat times change of temperature, is the change of temperature. And the way that becomes negative is by switching. So instead of T final minus T initial, whenever you distribute the negative sign, it becomes T initial minus T final. And so that's going to be MC times T initial minus T final. But instead of making a massive equation using this, what I'm going to do is kind of simplify it just a bit. So because we're allowed to use substitution in our problems, I'm just going to set up a column. So this is this column is aluminum, and this column is water, and this column is stirrer. I could call it copper, or I could call it stir. And this column right here is silver. So these are my columns, and I'm going to get the mass, the specific heat, the final temperature, the initial temperature on all of these, and I'm going to calculate what Q would be for every single one of these. And so the mass of the aluminum is what we don't know. It's what we're trying to solve for. So the mass of the aluminum we're trying to solve for, the mass of the water is 0.225, so that's 225 grams turned into 0.225 kilograms. The copper stirrer, 0.04 kilograms. The silver, 0.42 kilograms. The specific heat of each of these, aluminum is 900. You can get these from the chart. That chart happens to be right down below here if you're on my blog. If you're not on the blog, again, click in the description and you will find a link to this blog post. And so the specific heat of water is 4,186. The specific heat of copper is 387, and the specific heat of silver is 234. Now the final temperature is easy because they all have the exact same final temperature when they come to equilibrium. They're all at 32 degrees Celsius, and so you can just write that on across, 32 degrees. The initial temperatures, however, were a bit different. So the aluminum, the water, the copper were all at 27 degrees initially, and then we had this hot piece of silver dropped in that was at 87 degrees. So I'm going to set up a column that's the change of temperature, and the change of temperature 5 degrees, 5 degrees, 5 degrees, and 55 degrees. And so now I'm going to set up a column that's Q. I can't figure out Q for my aluminum yet, but I'm going to keep the numbers there because I will need those numbers. But the Q, if you plug in Q equals mass times specific heat times change of temperature for all of these, you'll get the energy transferred by water was 4,709.25. For copper, it was 77.4. And the energy transferred by silver was a negative 5,405.4. So just keep in mind that that is positive Q for each of these. And in our equation, we're going to switch that to negative Q. So our equation again, Q1 equals negative Q2. That's not plus, it's minus Q3 minus Q4. And so we can expand Q1 by substituting in for the definition. So we get the mass of aluminum times the specific heat of aluminum times the change of temperature of aluminum is equal to negative Q2 minus Q3 minus Q4. And then we want to find out what the mass was, so we can divide by the specific heat times the change of temperature, and we'll get that the mass of aluminum is equal to negative Q2 minus Q3 minus Q4 divided by the specific heat of aluminum times the change of temperature of aluminum. And since we've already solved for all of our Q values, we don't have to plug in MC change of T, we can just substitute. And so we said that Q2 was water, so water negative 4709.25. So negative 4709.25 minus 77.4 for the copper stirrer, and then minus a negative, so minus negative 5,405.4 for the silver. And then we're going to divide that by the specific heat of the aluminum, so that's 900 times the change of temperature of aluminum, which we said was 5 degrees Celsius. When you plug all of that in, you should get that the mass, so this all equals the mass of aluminum. So we should get the mass of aluminum is equal to 0.1375. If you're doing good record keeping, you'll know that that's in kilograms. And so it wants the answer in grams, so you'll just multiply that by 1,000, and you get, by 1,000 you get 137.5 grams.